Hey, so you may be wondering, what the heck does the study of rocks have to do with sustainability? Well, that's one of the things we're going to explore in this next class, which we're going to talk about and begin to get into the natural cycles of how the Earth works. And so topic 5 is the rock cycle in plate tectonics. Now that we've been through the building concepts of the pressing problems for planet Earth, generational approaches to problems, the IPAT equation, the scientific method, the tragedy of the commons, those have been our fundamental concepts, our building concepts for getting into understanding then how the Earth works, and then followed by how human activity has impacted the Earth and its sustainability. So our learning objectives for this portion of the course is to understand the following: how the three major rock types form, how plate tectonics works and how it accounts for a variety of Earth phenomena, and how a knowledge of the origin of rocks and the structure of the Earth and how plate tectonics work are important for understanding how to sustain a planet. So, always fair to ask the question, no matter how far afield or close afield the topic seems, why bother? Why should we bother investing our time into studying this? Well, if we consider this diagram that shows the atmosphere, the hydrosphere, the lithosphere, and the ecosphere, the lithosphere represents the surface of the Earth and its interior. All of these things interact, all of these spheres. Much like when we talked about the pressing problems for planet Earth, remember we talked about how we really can't keep them in their little cubby holes in that chart or that table where each problem was, that one key thing that table didn't really show us was how each of those problems are synergistic and interact. In the very same way, we can conceive of the Earth as these, and its living system or ecosphere, as this interdependent set of spheres. The lithosphere is also a repository for water, mineral resources, fossil fuels, energy. We'll discuss that as well. And the lithosphere can also be a driver for climate change, how things in the lithosphere change, how they change climate. A later topic, climate change through time, we'll examine that in detail. And in another later topic, we'll also see how the lithosphere actually provides records of past climate change. So given all of that juicy synergistic stuff, I think we're going to march forward and say, yes, we should bother with this. We're going to start with the most basic building blocks of Earth materials. They're elements and compounds, right? An element is any material that's comprised of only one type of atom, and it's distinguished by its unique atomic number. A compound are substances whose molecules contain atoms of more than one element. So here what's shown are oxygen, carbon, and hydrogen atoms. Remember, an atom being the smallest component of an element, having the chemical properties of that element. And we could see the simplest arrangement, H2O, makes water. We could see glucose, a more complex organic molecule, has all three, oxygen, carbon, and hydrogen, and in different proportions. The proportions that's unique to glucose is what makes it that particular compound. Minerals, by contrast, can be defined as a naturally occurring inorganic compound or element with a specific chemical composition and a repeating crystal arrangement. So let's take an example of what that means, how we can see it. So let's look at these quartz hand samples pictured here. We've got the purple stuff, which is amethyst. The building blocks of this mineral quartz is, in terms of chemical composition, silicon dioxide, SiO2. In terms of structure, it's the SiO4 tetrahedron, pictured to the upper right. So it's a silica ion in the middle and surrounded by 4 and bonded to 4 oxygen atoms. These tetrahedrons link together by sharing oxygens, and they can build up into crystals that we can see. So you see the linked tetrahedron arrangement is nothing more than a whole series of tetrahedrons that build up either in a chain or a sheet or a whole framework. And that's what makes up quartz. So now, by contrast, let's define a rock. Right? A rock is simply a naturally formed aggregate of minerals. So we've defined mineral, and now a rock, by comparison, is just an aggregate of those minerals put together. A rock need not have a specific chemical composition as a mineral does. What's pictured here is a hand sample of granite, and what you could see both in pictured there and also this hand sample of it here is that you can actually see the different mineral phases. There's pink, white, and black minerals in here. Pink is feldspar, which also is comprised in part of those silicon tetrahedron. The white is quartz, which we've just talked about, and the black is a mica mineral. And the mica mineral, in this case, is black. And you can see that all three of these minerals can be seen with the naked eye, and even better with some magnification. That makes up this particular kind of rock, which is granite. And there are three basic types of rock. Granite is an example of igneous rock. We're going to talk about the three main ones: igneous, metamorphic, sedimentary. Okay, so there's a hand sample of the granite. I was able to look with a magnifying glass and see the minerals up close. You could even see it with your naked eye. Another way we could study this is by looking at a thin section. Take a very thin slice of the rock, put it under a microscope, and there you could see the quartz, the mica or the biotite, that's the black mineral, and the feldspar. So let's talk about igneous rocks as the first rock type we'll look at. Now, igneous rocks form by the freezing of hot liquid magma. If they don't make it up to the surface of the earth by the time they cool, so the magma forms at depth, and we'll talk about that, how that happens later. The magma forms, it's molten rock, it forms at depth, it rises up towards the surface of the earth. As it gets towards the surface of the earth, the surroundings get cooler and cooler. If it gets cool enough, the magma will freeze, and it will crystallize and turn into a rock. If it takes a long time for that magma to cool down and freeze, it will grow big crystals like we saw in the hand sample of the granite. If it goes shooting up to the earth really fast, like during a volcanic eruption, then we call that an extrusive rock. It makes it to the surface of the earth where it's very cool relative to the interior of the earth where the magma started, and it freezes so quickly, like in the blink of an eye, but actually longer than that, so quickly that there's not time for the crystals to grow. And what we see in this case, in this sample of basaltic obsidian, it's very glassy. No minerals are able to form, so it actually just quenches, as we call it, and converts from magma into this glassy, non-crystalline structure. Okay, so this is an extrusive igneous rock. It came out of a volcano because it cooled very quickly. This is an intrusive igneous rock because it intruded into the earth, didn't make it all the way out and extrude from the earth. So how do these magmas, you may be wondering? Somewhere around range, a good range magmas is about 700 to 1300 degrees centigrade. It's where most magmas form at. Volcanic eruption will bring this right up to the surface of the earth, and it'll go from therefore somewhere around 1000 degrees centigrade to the surface of the earth, which is around 25 degrees centigrade. No time in that quick freezing to grow big crystals. All right, and we could see examples of extrusive igneous rocks if you've been to any volcanic part of the world, whether it's Iceland or Hawaii. Really great examples of that. Intrusive rocks, we have some pretty close to home here. If you've ever been out to Enchanted Rock in Central Texas, you've been on a big igneous dome, about 1.1 billion years old. So if you've wandered over Enchanted Rock, you've trod over a surface that's over 1 billion years old. Pretty mind-boggling. You may be asking, wait, you said Enchanted Rock was an intrusive. Yes, it is. It's a granite intrusive rock. But it's at the surface of the earth. Well, when it intruded 1 billion years ago, it was deep below the surface of the earth. And subsequently, over 1 billion years, there's been enough erosion that has actually brought Enchanted Rock up to the surface of the earth. We've been through igneous rocks. Now we're going to talk about another major rock type, sedimentary rocks. And these rocks form from the chemical erosion and the physical erosion of other rocks. So you could take an igneous rock, or the third type of rock we'll talk about, metamorphic rock. You take them and weather and erode them, and you create new rocks by deposition of sediments. And then those sediments get cemented together through a process of burial. They get lithified, and they become hard rocks. They go from loose sediments to hard sedimentary rocks. If we move on to look at environments of deposition of sedimentary rocks, of where these sedimentary rocks form in, we could see that in this 3D block diagram. It gives you a view from above, and it gives you a view from the side. A couple of major things here to note. There is a mountain range, and on the upper or left side of the mountain range are arid conditions. To the right or lower from the mountain range on towards the sea, those are more humid conditions. These different environments produce sedimentary rocks with different kinds of characteristics. There's also different environments here, not just in terms of the climate, arid versus humid, but the settings in which they form. Continental sedimentary rocks versus marine sedimentary rocks. That's as simple as it sounds like. Continental sedimentary rocks form on the continents. Marine sedimentary rocks form in the ocean. You've been to many of these environments that are being shown here. If you look around, you go from sand dunes to desert dry lakes to floodplains to deltas to lagoons to reefs to continental slopes. I'd wager many of you have been to many of these environments. The sand at South Padre Island that you've walked along is that lagoon/sandbar environment that's shown along the coast. If you've been to New Orleans, you've walked through mud, or you've walked through a city that was built on top of the mud and sand of the delta of the Mississippi River. That's shown in that delta location. The sand dunes back behind the mountain range, if you've ever been to White Sands National Monument near Alamogordo, New Mexico, you've been on those sand dunes. The reefs that are shown here, if you've been to the Bahamas or the Caribbean and have been snorkeling over a coral reef somewhere, you've been to that marine sedimentary rock environment. And let's look at two ways that you can make a sedimentary rock. Now here's another 3D block diagram. Let's define weathering and erosion here as the physical and chemical processes that break down rocks. Physically, how does that happen? Wind and water. Chemically, how does that happen? Well, it could be the dissolving power of rainwater, soil water, groundwater, surface water. So we can chemically erode and weather, or we can physically erode and weather. And however we do it, what we can do is take pre-existing rocks and break them down and create new rocks. So you see that as the transition from pre-existing rock to new sediment, that's the process of erosion and deposition. Okay, so two ways to make a sedimentary rock. Let's go through way one. So way one is you deposit grains, could be sand, clay sediment, from the breakdown processes, erosion, of pre-existing rocks. They then solidify upon burial to make a rock. It goes from sediment to sedimentary rock. You make a sandstone or shale the way that's shown here. So a quick review question. New sediments get buried and lithify. What is that? Yeah, sedimentary rock. Okay, now let's go to way two. Chemical precipitation in water is the second way we can make sedimentary rocks. And in this case, mostly what's going on is you got critters, different creatures, organisms living in the ocean, in lakes. They make skeletons, they die. The skeletons are made out of mineral, in most cases calcium carbonate. That mineral settles down to the bottom of the ocean or the lake and accumulates. So as an example, we can look at coral reefs. Coral's an animal that creates a skeleton made out of calcium carbonate. It takes calcium and carbonate ions from seawater and it secretes a skeleton. Here's a big chunk of a coral, Montastria annularis, the common star coral. It's from the island of Barbados, and this formed in the ocean back when this part of the world was under the ocean. And you can see all the little holes in there. It's a colonial organism. Every one of those holes is where the living tissue was. But what I've got in my hand, a really hard rock that if I struck you with it, you'd be very insulted because it would hurt a lot. This is not a soft sediment. This is a hard lithified sediment. If any of you here have, or any of you watching, have been to places such as the Guadalupe Mountains, in West Texas and New Mexico, there was similar reefs being built in marine sedimentary environments when the ocean covered that area 270 million years ago. You could actually see all of these sedimentary environments like we just looked at on that block diagram. Just about all of those can be seen if you go to the Guadalupe Mountains today and walk along the Permian Geology Reef Trail. Okay, so sedimentary rocks are important because they're reservoirs and aquifers. They're reservoirs for fossil fuels like petroleum. They're aquifers for fresh drinking water. They occur in sedimentary rocks. Here's another 3D block diagram. We're going to look at the front face. It's mostly a cross-section here. And what we see is in this cross-section, we see limestone is that block pattern, shale is that sort of dash pattern, and sandstone is that stipple pattern. What we see is that the limestone and sandstone contain the petroleum. The shale does not. The shale is relatively impermeable. We could look at examples of why that's the case. So here's an example of a limestone. This is actually a piece of the Edwards Aquifer. And take a look at those honking pores in this rock sample. Those are gigantic pores. I don't need a hand lens or anything to see those. I could stick my finger into some of these and get it stuck. I could also use magnification and see a whole series of smaller pores as well in this sedimentary rock or limestone that's made up of a bunch of sea critters that died a long time ago. So this was way two, chemical deposition, that this sedimentary rock was made. The important point here is it's highly porous. Now if we look at another kind of sedimentary rock that's made out of mud particles that lithify and become a sedimentary rock, that's called a shale. if you look at this shale, no matter what way or angle that you look at it, and could use magnification and look at it till the cows come home, there's very few, if any, pores can be seen. This is a very unporous rock, and the pores not only are very few, they're not very well connected, and we call that impermeable. So because it's impermeable, it actually helps trap petroleum deposits. So petroleum is less dense than water. It tends to rise up through a sedimentary section, and in this case it's getting trapped by the impermeable shale. That's that impermeable rock made out of original mud particles that lithified, became the sedimentary rock known as shale, and now is serving as a barrier and a way to trap hydrocarbons or petroleum, fossil fuel deposits. So one thing that we'll return to over the course of the semester is how important the porosity and the connectivity of those pores, a characteristic known as permeability, how important that is for understanding when sedimentary rocks are reservoirs and when they're barriers to being reservoirs. The last kind of rock type we're going to look at is metamorphic rock, and that's simply taking a pre-existing rock of another type, sedimentary, igneous, and altering it by high temperature and pressure. When you alter it, you can change the texture, you can change the composition, you can change both. Take a look at this metamorphic rock, and take a look at the sort of the linear nature of these dark minerals that are lined up here. Remember the granite sample, in which this was the igneous rock, in which things seem to be more randomly oriented. In the metamorphic rock, in my left hand, you can actually see that there's a preferred alignment. The forces of the pressure actually line these minerals up deep below the surface of the earth. Pretty cool. Modifying the texture to go from an igneous to a metamorphic rock. Okay, we put all these three rock types together in this grand diagram called the rock cycle. Most of you should be familiar with it. But let's start at the very top where we have weathering and erosion. We're weathering and erosion, we're making sediments. Those sediments are getting buried, lithified, and they're becoming what? What is that? Yeah, sedimentary rock. If you bury them deeply enough, they don't just become lithified sedimentary rocks, they can metamorphose and become metamorphic rocks. If you bury them really deep, subject them to high pressure and high temperature, you can actually melt those metamorphic rocks and they'll become magma. The magma then can rise because it's less dense and buoyant. It rises and it cools and it becomes an igneous rock, whether it's intrusive or extrusive. We're not going to worry about that right here. So then what happens is you take all those rocks, you see all those lines, all those arrows designated uplift. You take the sedimentary rock, the metamorphic rock, or the igneous rock, you uplift them all. What you do when you uplift them is you subject them to weathering and erosion, and then you start the cycle over again. Right? Every rock is destined to ultimately become another kind of rock, given enough time. Given enough time? Well, 4.5 billion years of Earth history, we can put these rocks through the ringer and cycle them from one kind of rock to another kind of rock. All these uplift processes we haven't talked about. It's just this word, uplift. How does that happen? We're going to talk about that when we talk about plate tectonics. Okay. To check if you understand the rock cycle, you should be able to sit down or stand up, really. It doesn't matter whichever way you do. You should be able to sit down and basically, without looking at that diagram, just reason through how it works. Without looking at it, you should be able to draw it and reconstruct it, starting with weathering and erosion, taking rocks, making sediments, making metamorphic rocks, making igneous rocks, uplifting them, and turning them back into sediments. So weathering and erosion have also very important roles in controlling the composition of the hydrosphere and the atmosphere. So it's another reason why we worry about rocks and the rock cycle in terms of sustainability. Our water resources, our atmospheric resources are directly dependent. Their composition and quality are directly dependent on how they are interacting with the lithosphere. Now, when we talk about plate tectonics as we move forward, we need to understand the structure of the Earth. So we're going to go now from the rock cycle to talking about a cross-section through the Earth and what it would look like. We want to understand the Earth's cross-section and what it looks like, both chemically and physically. So there's two ways to actually look at a cross-section through the Earth, and it would have a slightly different structure depending on what we choose. First are the chemical characteristics. So the chemical characteristics, the main components here of interest are the outer crust and the mantle. The core is at the ultimate center of the Earth, We're going to concern ourselves just with the mantle and then the crust on the outside. So over Earth history, there's been movement of material as magma from the mantle to the crust, and this has actually changed the composition of both the mantle and the crust over time to what we see today. And in fact, those compositions, because those magmatic processes of sending material from the mantle to the crust, still continue today. So the Earth's crust and mantle composition continue to evolve. These are slow processes, nothing along the lines of things we're looking at in terms of climate change, as an example. All right, so let's start now, turn to, instead of chemical characteristics, let's consider the physical characteristics of a cross-section through the Earth. We have the outer lithosphere, which we've talked about. Then the next layer down is called the asthenosphere. The next layer down is called the mesosphere, or if you want to sound really cool and nerdy at the same time, say mesosphere. And then we get into the outer core and the inner core. So let's start with the lithosphere, the outermost layer. We say outermost, it's not like it's the skin. It goes down 100 kilometers deep. It's the outermost Earth layer. It's a brittle solid, so if we took it, banged on it with a hammer, piece of lithosphere right here, it would crack. And we'll see when we get deeper in the Earth, the rock actually won't crack if you hit it with a hammer. It will actually flow. That would be when we get to the asthenosphere. So in looking at this cross-section of the Earth, it's really interesting to note that the deepest drill hole we've got, how far down have we gone? How far down do you think we've gone? Do you think we've gone all the way to the bottom of the lithosphere, 100 kilometers down? We've actually only been 15 kilometers down. That's a really deep drill hole. Another way we could tell things about the structure of the Earth is through seismic waves. Those are waves generated by earthquakes. Those are waves we can generate at the surface intentionally by banging on the Earth. So we have an earthquake, or we come along and bang on the Earth, stuff like that. It actually sends, if you do that, not only does it hurt because I'm doing it loud enough to be heard, it actually hurts my hand, but it's also sending waves through this desk. Similarly, when there's an earthquake, it sends waves, seismic waves they're called, propagating through the Earth, and when they hit different kinds of material, whether it's brittle or ductile of a certain composition, those waves actually get bent differently. And then when they come up to the surface of the Earth, you can actually see where they are, and then you can infer, if you know where the earthquake was, what path it took and what kind of material is through there. Sometimes it goes fast through certain material, slow through other kinds of material. And so that's kind of a detective kind of way to put together what a cross-section through the Earth looks like. So we're at the lithosphere, now we're going to go into the asthenosphere. And as you go deeper down into the Earth, you go to higher pressure, higher temperature. And in the asthenosphere, the temperature and pressure are in a very delicate balance right near the melting point of the rock material down there. So as a result, the rocks aren't solid. They're too close to the melting point. They're more plastic or ductile. They kind of flow. And at the surface of the Earth, the same composition rock can be a hard rock. I'm not going to hit my head with it, but if I could, if I wanted to, and draw blood. But if I had a piece that was from the asthenosphere, it wouldn't draw blood because it would be nice, soft, and ductile. It would be over 1,000 degrees, so I'd have other problems I'd have to deal with. But you get where we're going with this. Very different properties of rocks because of the different pressure and temperature regime down there. High temperature, high pressure, the rocks flow easily and then are deformed, and that's where volcanic activity originates. If we go even deeper, we get into the mesosphere. There, the pressure is so high, it offsets the higher temperature effect at this point. And as a result, the rocks gain rigidity and mechanical strength. And the rocks down there in the mesosphere are solid and rigid. So they're solid and rigid at the surface of the Earth, the lithosphere down to 100 kilometers. You get to the asthenosphere, they get soft and plastic. You get further down into the mesosphere, and they get rigid again. So let's review really quickly. Physically, the Earth's interior changes from brittle to ductile as a function of depth. Brittle, breakable, ductile, flowable, as a function of the pressure and temperature changes with depth. And chemically, the Earth's interior changes from a silicon-rich crust to a magnesium-rich mantle. And that's a result of melting in the mantle and melt movement up into the crust. Okay? Now we're armed with a bunch of information about what a cross-section through the Earth looks like physically and chemically, what the rock cycle looks like. And now we're going to take this information and apply it to this fascinating theory known as plate tectonics. And see you in class to do that.